Hi, I'm Jungwook from IBM Research AI. It's an honor to be here to present our recent work on accurate and efficient 2-bit quantized neural network with Swagas, Vijay, Kailash, and others. Here's an overview of my talk. I will start with the motivation of why we are focused on quantized neural net. Then I will present our QNN strategy, parameterized clipping activation for activation quantization, statistics-aware weight binning for weight quantization, and quantization in the presence of shortcut connections. Then I will explain how much system-level performance we can gain using our proposed schemes. Then I will conclude. We've been witnessing breakthrough in AI that starts to achieve human-level intelligence. Recently, IBM Watson and Google AlphaGo have surprised people with their outstanding performance on Jeopardy quiz show and Go Play. But this success is at the cost of intensive energy consumption. If we compare their energy savings, energy efficiencies with the human brain, there is still a huge gap. So to truly achieve human-level performance, the current AI needs to be more energy efficient. The conventional way of improving performance and energy efficiency is by scaling down the transistor size. But as the Moore's law is ending, the progress there has been slowed down. Instead, in IBM, we have focused on precision scaling with the rule of thumb that the reduction in bit precision results in quadratic energy savings. So starting with the first demonstration of 16-bit DNN training in 2015, we reduced the bit precision down to 8-bit for training and 4-bit for inference. And today, I will share our recent achievement of 2-bit DNN inference using quantized neural network. So quantized neural network is to train a model that can exploit precision reduced activation and weight. The overall training procedure is the same, but the key difference is that the impact of quantization is incorporated in the training so that the network can adapt to the quantization error and become robust. There has been extensive work on quantized QNN, but most of them focused on expensive quantization schemes that results in slow training procedure and inefficient arithmetic unit. And some of the work tried to compensate the accuracy degradation by enlarging the network size, but that results in increased computational complexity. In our work, we focused on accurate and efficient quantization schemes so that we can truly take advantage of the system level QNN for the system level performance. So there are 3 schemes I'm gonna present. First is activation quantization, which automatically tune the clipping level to balance clipping and quantization error. And weight quantization, which exploit weight statistics to better capture the shape of the weight. And quantization in the presence of shortcut connection, which enhance gradient flow of training by not quantizing the shortcut. So let's start with activation quantization. So the challenge in activation quantization is that there is a trade-off in activation functions when we apply quantization. So output activation after ReLU tends to have large dynamic range. As you know, ReLU is the most popular activation function in CNNs, but if you directly apply quantization, then you will suffer large quantization error. As an alternative, a static clipping function has been proposed, like ReLU6, which take the large magnitude value be clipped by a fixed threshold, so that you can reduce the quantization error, but there is some information loss when the large magnitude activation is clipped. So there's some. So if you don't quantize, the value works best. But once quantized, value the network with value failed the convergence. Clipping function works better, but still there is a significant accuracy gap. So we can empirically show that there is a trade-off between clipping error and quantization error as the clipping level changes. But it's really hard to find this sweet spot because this is different for different layers and changes over training time. So our idea is to auto-tune, automatically find this sweet spot by training. So we proposed a new activation function called parameterized clipping activation, PACT. In PACT, clipping level alpha is trainable parameter so that it's auto-tuned by the backpropagation. So this figure shows the function in the 4 paths and the gradient. So as you can see, if your clipping level is lower than some proper output activation, then it is guided to be increased. So we initialize alpha as a large value to emulate the emulate value, but we regularize alpha with the L2 regularization so that it converges quickly to the small value. As you can see, there are different alphas for different layers, which is very different from the static clipping function. So, so we can empirically show that PACT could find the sweet spot that achieves lowest error. Let's move on to weight quantization. In weight quantization, the goal is to find the quantization scale alpha W that minimizes the difference between the true W and the quantized one. The previous approach uses the first moment of W, which is the represented value for this distribution. For example, XNOR uses this first moment to come up with the analytic solution as a function of mean. But the drawback is that the first moment cannot capture the shape of the distribution well. So we needed to find a way to better characterize the weight distribution. The idea was to employ not only the first moment, but also the second moment, so that we can capture the overall shape as well. We conjecture that by having these two statistics, we can characterize alpha as a function of the linear function of the sort of standard deviation and mean. To validate this idea, we find alpha, the best alpha, for six different representative distributions and plot it together in a one plot. Surprisingly, we observed that they are all aligned well with the line, indicating that alpha can be almost fully characterized by these two statistics. So by linear regression, we can find this coefficient, and using it during the QNN training, we just need to compute mean and standard deviation and come up with the alpha for quantization. This slide just to show how general our approach is. So we can extend our weight quantization scheme for multi-bits. And you can see that in all cases, the optimal alpha aligns well with our heuristics. And we can empirically show that compared to the optimal scale, our heuristics can achieve equally accurate quantization. So the last point, let me explain the quantization in the presence of shortcut. We observed that when we apply quantization to feed-forward network like VGG, it was quite robust. But when we apply quantization to the network that has shortcut, like ResNet, there was huge degradation. After thorough investigation, we found that the shortcut is very sensitive to the quantization. The shortcut is the path to flow the gradient in the backprop, but once it's quantized, then it suffers diminishing gradient problem. So as you can see, if we measure the magnitude of the gradient, when shortcut is quantized, its magnitude becomes so low. So we propose not to quantize shortcut, and the good thing about it is that its computational overhead is just 1%, so that it's negligible in terms of overhead. So by not quantizing shortcut, we could recover the magnitude of the gradient so that we could train the quantized neural net better. So all things together, we could achieve less than 1% degradation for CFAR10 ResNet with different depths. And also we could achieve like one of the lowest accuracy degradation and one of the highest absolute accuracy for both CFAR10 dataset and ImageNet dataset. So for CFAR10 dataset, we tried ResNet 20 as well as VGG. And also for ImageNet dataset, we tried AlexNet, ResNet 18, and ResNet 50. So these accuracy number was higher than the accuracy number reported to date. So far we covered our quantization schemes. The question then is how much performance we can really get from the system out of this quantization. We can always say that in high level there will be significant gain, but given the constraint on bandwidth, on-chip memory, and area, there's some limitation in the gain as well. So to better understand the overall performance impact, we employ a bandwidth-centric performance estimation model, which consists of set of cores, each of which is equipped with 2D systolic array with the fixed point MAG unit inside. The goal is to estimate effective throughput given area and on-chip memory and off-chip bandwidth constraints. And the peak, since the total area is fixed, the peak throughput is determined by the max per area, which can be increased as we reduce the bit precision. So we compare the inference speed for ResNet 50 with varying bit precision. And for the large bandwidth scenario, we could achieve almost linear speedup for bit reduction. And for extreme case, there's some inefficiency in data mapping because there are so many data items when we reduce the bit precision to 2-bit. But this is the case when the bandwidth is very large, so that getting the data from the off-chip memory is not that costly. But when we reduce the bandwidth to 32 gigabyte, we can observe interesting scenario where for the reduced precision case, we can achieve a super linear speedup. This is because the lower the bit precision, the more items can be fit into the on-chip memory, so that it can increase the data reuse. So from this work, we could conclude that our quantization scheme can improve not only throughput, but also data reuse to achieve high speed up. So one thing to note is that our quantization scheme does not increase the computation of the network to compensate the error. So compared to the case when which relies on such an enlarged network for a robust accuracy, we could further achieve 2 to 3 times speed up. So in conclusion, we discussed that quantizing activation and weights is critical for high performance and energy efficient DNN inference. So we propose novel quantization techniques, both weight and activation. For parameterized clipping activation, we explained that we can tune the clipping level by training to find the sweet spot automatically between the quantization error and the clipping error. For weight quantization, we propose statistic-aware weight binning, which exploits the first and second movement of weight to better capture its distribution and reduce the quantization error. And also, we further propose full precision shortcut so that we can maintain the efficiency in training convergence. So we demonstrate accuracy and system performance gain on for the proposed QNN schemes, which improves the throughput and data reuse and achieve 2 to 3 times speed up over state-of-the-art QNN scheme. So that's all for my talk. I will happy to get any questions. Thank you.
Okay, we have a couple of minutes for questions.
Harris Teague from Qualcomm. Can you say a little bit more about PACT and how the alpha is chosen, how you make it differentiable for training it as a parameter?
Sure. So our PACT function is a composition of this absolute function, and we take. Oh, sorry. So we use state through estimator for the backpropagation. So the derivative for this quantization can be estimated, and further the derivative over alpha can be defined like this. So when the output activation was larger than alpha, then the gradient is 1. Otherwise, it's 0. And there is initialization and the regularization to make it work better. So, yeah, no problem.
Hi, Rick Kaye with Microsoft. Just curious, have you applied this technique to already compressed networks, or do you have an intuition around, if you applied it to SqueezeNet or ENet or something like that?
So there's some ongoing work of applying these techniques to other networks, like MobileNet and DenseNet, and I think we don't cover SqueezeNet, but and LSTMs as well. And we hope that we can have more progress on there and publish to the conference again.
Okay, great. Let's thank our speaker again.